going to talk about accelerating sequential consistency for Java with speculative compilation. Thank you.
Hello, everyone. Today I'm going to talk to you about how to make your program safer and also worry less about memory order constraints of your programs by slowing your program down. So we all know Java is a safe language. It is memory safe and it is type safe. However, there are also examples in Java that are not so safe. So our example here is quite similar with the example just shown by the previous speaker. Here we have two threads. One thread is producing an object. Another thread is trying to consume that object by calling a method on that object. By the first look at it, this looks perfectly fine. Thread U here is first doing the necessary null check on the object to see if the object has finished initializing. And only after then, the thread U will call the method of that object. However, under the current Java specification, this implementation is problematic because it is possible that when thread U is at 9.3, the object is still being constructed. In that case, thread U is seeing a partially constructed object, which is a security vulnerability. I'm not going to go into details to explain why this will happen, but general idea here is that Java specification allows compiler or hardware to order memory instructions. And if these two instructions in the constructors gets reordered, then we come to this unfortunate scenario here. So according to the current Java specification, the way you're supposed to fix it is that you're supposed to declare the field P as volatile. In Java, if you declare some field as volatile, there will be no observable reordering with respect to reads and writes to the field. And by that, you can have the expected semantics of your program. So if you have other examples like this in your programs, you also have to annotate other fields as volatile. So again, this may look like a case where the programmer just made a mistake, where the programmer just forgot an annotation. But if you think about it, the problem is bigger, because the root cause of this problem is that Java does not guarantee program order by default. And because of that, the burden is placed on the programmers to use annotations all over their programs to get back this program order guarantee. And we believe this is a bad practice because this goes against the principle of safe languages. For example, we say Java is memory safe because this goes against the principle of safe languages because safe language should protect its abstractions by default. For example, we say Java is a memory safe language because Java protects the abstractions of memories. That you have abstraction of isolated logical variables that even if the programmer made some mistakes, you don't have buffer overflow. And another example here is that Java is type safe because it protects the abstraction of types by default. That only certain types of operations can be applied to certain types of objects. So if you follow the same line of thought, if you believe program order is an important abstraction, you should try to protect it by default. So here's when the concept of memory model comes into play. So memory model of language defines the possible value that a shared memory read may return in a multi-threaded program. It basically tells you the ordering constraints of memory reads and writes in your program. So there are strong memory models which gives you stronger guarantees of the program of the ordering of instructions, and there are also weak memory models which gives you weaker guarantees. And one of the most intuitive memory model is a strong memory model called sequential consistency. And in sequential consistency, all programs are guaranteed to obey the per thread program order. So this is very easy for programmer to understand. So therefore, if you want to protect program order, you should get sequential consistency. However, as I just showed before, Java does not provide sequential consistency. And not only Java, most of mainstream languages do not guarantee sequential consistency. And the reason of that is that people are worrying about performance. So just as all the other good things in the world, safety guarantees in a language always come with a cost, and that cost is performance. And in the case of sequential consistency, if you want to guarantee sequential consistency for a language, if, for example, for Java, you will need to first restrain compiler optimization to avoid reordering certain instructions. And the second, you also need to insert fences in the generative code to prevent hardware from reordering certain instructions. And by doing those two things, you're going to slow your program down. So this is inherently a performance safety trade-off here. You want safety guarantee, you also don't want to slow your program too much. So this is all fair enough, but what is actually the cost of having this safety guarantee? We should just get the cost first and then start and then debate if it's worth it or not. Surprisingly, very little is known about the actual cost of SC on today's hardware and on modern VMs. It's just the kind of things that people just always assume that's the case, that SC is going to be too expensive. However, there aren't many empirical studies of the giving out practical numbers of the cost of SC for modern VMs. Therefore, we decided to start out and try to measure this. We implement this prior work for x86, where we propose this new semantics called volatile-by-default semantics. In the volatile-by-default semantics, all heap accesses are treated as volatile by default. Therefore, you can have sequential consistency at a bytecode level by default. So we implement these semantics for x86. We try to get practical numbers, so we choose a production JVM, the HotSpot JVM, from which is used in both in Oracle's Java and also OpenJDK. And we implement these semantics, and we measure the performance cost of it for the DaCapo benchmark. And from our evaluation, we show that there's actually 28% of overhead on average for the DaCapo benchmark, which is a moderate cost, and much less than people have expected. Now, after we have this result, a normal question we get is, what about ARM? So ARM is another kind of architecture that's commonly used, but it is also much weaker than x86, meaning that the ARM architecture we are now much more reordering between instructions compared to x86. Therefore, if you want to have sequential consistency on ARM, you're going to have a higher overhead than x86. So to answer this question, again, there's only one way to find out, that is we have to actually implement it and to measure it. So this is what I'm going to talk about today, that we actually implement SCJVM, and also we optimize it. So again, we try to get practical numbers, so we just choose to use HotSpot JVM for the ARC64 port. So the first thing we did is that we try to get a baseline number of the cost of SC. So we implement this JVM, which we call VBDA-HotSpot, which use the similar implementation technique as the previous work on x86. Basically, we treat all the heap access as volatile and to measure the performance. So to the best of our knowledge, this is the first study of the cost of SC on a production JVM on ARM. So we did several different interesting evaluations. Just to give a quick highlight of the results here. Basically, here I show the results for the DaCapo benchmark, and we tested on a 96-core ARM server, which has a Kelvin Thunder X CPU. And here, y-axis shows the relative execution time over the baseline HotSpot JVM. So the lower, the better. So from the result here, the average overhead is 57%, which again is less than what we expected. But if you look at the maximum overhead here, is 157%, which is quite high. So we also want to get out to actually optimize the implementation. So there are some existing work trying to reduce the cost of SC for languages. However, many of those prior work, they rely on techniques such as offline whole program analysis. In a modern VM, where you have state-of-the-art techniques such as dynamic class loading and JIT compilation, there is really limited effectiveness of such techniques. Therefore, we implemented two novel optimization here. The first optimization is speculative combination technique. We use this technique to remove the fancies for thread local objects dynamically, which I'm going to talk a bit more later. The second optimization here is that we also noticed that in the baseline HotSpot JVM, the implementation of volatile insert fences to prevent both to prevent reorderings between volatile accesses and also the reorderings between volatile access and the non-volatile accesses. But in a volatile by default world, everything is volatile, so there's no need to insert additional fences to prevent reorderings between volatile and non-volatile accesses. So that's how we can reduce the fences we insert, and as a result, we can optimize the implementation of SC rights. So just to give you an overview of the results here, again, we're measuring the cost on the DaCapo benchmark. And as you can see here, with both of those two optimization combined, we're able to reduce the cost of the DaCapo benchmark from 57% on average to 37% on average. And this is on ARM hardware. So this is more than a third of the reduction. And if you look at some of the example here, there's even higher reduction for the benchmark that was having a higher overhead. So all of the implementations, they are open sourced. You can find it on GitHub and also ACMDL, and also this whole thing is artifact evaluated. So due to time limit today, I'm going to just talk about implementation of the speculative compilation. So there are a lot of interesting details of the baseline implementation and also the other optimization. If you're interested, we can discuss later, or you can find it in the paper. So let's talk about optimization here. So again, the motivation here is that the traditional optimizations to reduce the cost of SC doesn't really work if you have the JIT compilation or dynamic class loading. And the solution we give here is that it's a JIT-based technique which we call a speculative compilation. The basic idea here, imagine we have two versions of code. For every method, we either have a fast version of code where there's no additional fence needed, where we can keep all the compiler optimization there, and which they have the current Java memory model semantics. And we also have the slow version of code where there we need to insert necessary fences. We need to disable certain optimizations to have the volatile-by-default semantics. So the basic idea here is that all the objects will start off executing the fast version of code. And we will dynamically switch to the slow version of code when necessary. So this is just a high-level idea. Now, before this can be actually implemented as a actual implementation, there are a few high-level questions we need to answer. The first one is, when are we going to switch to execute the slow version of the code? So when talking about sequential consistency, the most precise way of saying when you should execute the fast version of code and when you should execute the slow version of code is that if you don't have any data race, then you can execute the fast version of code. If you have any data races, you should execute the slow version of code. But if you want to execute that, that's not good because that's going to be too expensive. You're essentially going to implement a dynamic data race detector, which is known to have a high runtime overhead. So as a result, we decided to define that in our implementation, we are going to switch from the fast version of the code to the slow version of the code when an object is accessed by a second thread. So basically, we're saying if the object is thread local, then there's no need to insert any fences. If it is not, then we're going to execute the slow version of code with fences. Of course, this will only work if most of objects are thread local throughout their lifetime. So this is the hypothesis we have here, and it is actually later validated through our evaluation. Now, with that in mind, the additional work we have to do is that we have to track when this access is happening. And the way we do that is that we add an additional header word in the Java object layout to keep track of the creator's thread of each object. So therefore, I just start off executing this fast version of code. And before every heap access, I just compare my current thread ID with the creator thread ID of the object. And if they're saying that everything is good, if they're not the same, then we should switch to the slow version of code. And the second question here is that, as I mentioned, we must do this runtime check before heap accesses, and this maybe have a very high overhead. So it means that we need to do some optimization to reduce the checks as much as possible. Okay. So the basic idea here is that if you have consecutive checks on this object, then you don't have to have all of them because you're always the same thread. If the first check passed, all the consecutive checks will pass. So let's just explain this in an example, which is easier to understand here. So let's say this is your program, which have random access to different fields. And by the most naive implementation, you will need to have 4 checks here. But because I'm always the same thread and the creator thread ID of the object will not change, so you don't actually need 4 checks. There's 3 checks on these objects here. You can actually just have 1 check at the beginning of the method and then just reduce number of checks. Notice that the correctness of this implementation is actually not as obvious because there are also some nasty racy situation here, but we take care of that, and you can check that in the paper. So the third question here is that how are we going to switch from the fast version of code to the slow version of code? The way we did it is that we do it on a per class basis, meaning that instead of keeping 2 versions of code at the same time and decide which one to call dynamically, we only keep 1 version of code for each compiled code. So it is either fast version or the slow version. So it means that we should have a way to safely and correctly switch during the execution. We have to invalidate the old compiled code and recompile again with the new code with the fences. So this is actually a more complicated procedure than you think, because these need to happen in the middle of execution. You need to take care of your own stacks, and you need to take care of the other thread stacks. Fortunately, there is a very similar procedure that's already being implemented in HotSpot JVM. So HotSpot JVM have this thing called a de-optimization. So in HotSpot JVM, when you first compile a method, you're going to make some aggressive optimization assumptions. And later, if these assumptions are being invalidated, you're going to invalidate and recompile, which is exactly what we need. So basically, we just reuse their technique and adding our own tracking of which method to optimize. So again, this is still very high level. There are much more details in the paper. So just as a result here, again, we tested on the DaCapo benchmark, and we tested peak performance using existing technique. And here I have 4 bars. The first bar is like the baseline SC implementation. The last bar is when both of the optimizations are enabled. And the middle 2 bar is only one of the optimization is enabled. As you can see here, both of the optimization contribute to part of the reduction of the overhead, but with both of the optimization, it actually get reduced to 37% ARM. I don't have much time left. I'll just quickly go over the related work here. So there are existing work trying to measure the cost of SC. Some of them they're for functional language like Haskell. Some of them they rely on offline whole program analysis, or they are relying on hardware support. So there are also kind of work that gives you stronger guarantee than SC, namely the language level region serializability, but we believe the cost of them is going to be higher. And also notice that most of the work they're using research JVM, such as like JAX-R VM, or they're focusing on x86. And so the third part is that there are also kind of work that provide you less guarantee than sequential consistency. Specifically, they're trying to eliminate the cost of out-of-thin-air reads. Therefore, let me just quickly conclude. We believe safe languages like Java should protect program order by default, just like they should protect memory safety and type safety. Although there is a performance cost here, we believe that the cost of SC should be measured first before people jump into any conclusion on this performance versus safety debate. And therefore, we took a first step. We measured the cost of SC on x86. We measured the cost of SC on ARM. We also took the first step to implement optimizations to reduce the overhead of SC on ARM. So the current result we have now is that the best we can do is on our ARM machine with 96 cores, we can have 37% overhead for SC. The long-term goal here, this is still a quite a significant number, but we want to remind you guys of memory safety. Think about memory safety. When GC first came out, it was also expensive. But after years of hard work of people in our community, it is now mainstream. And here, I just want to ask people to like help us in this case to work together a better future where SC is compatible even on weak hardwares. Thank you. I'm happy to take questions.
Thank you very much, Lun. We have time for a couple of questions, so if you please like to come to the microphone to ask.
Yathine Maniarka from Princeton. Nice talk. I noticed in your graphs that the Eclipse benchmark got worse with the
Speculative. Yeah.
Yeah. So what is it about this particular application that causes it to be worse rather than getting better with the optimization?
Yeah, so basically the speculative approach, there is a runtime overhead here because we have to perform a check, verify the access, and also at least one at the beginning of each method. So let's say if you have I don't have a clear answer of why that is the case, but now my guess is that, for example, if you have much short methods, and or in that case, you might not be getting much from the speculative approach here.
But you wouldn't be checking more times, would you?
This is compared to, so basically this number, the first part is the baseline implementation where I don't check any at any time. I just insert fences. So you're comparing a case of either you insert a fence or you have a check at the beginning of the method.
You guys follow up after?
Yeah.
Could the next speaker please come and get set up, and we'll have 2 quick more questions.
Thank you for doing, Jean Pichon, University of Cambridge. Thank you for doing this work. I'm really glad someone did this, but I'm very puzzled by your conclusion, because you say, 38%, that's okay. But yesterday at ISMM, there were like grown men crying tears of joy when they had 0.5% increases in performance. Do you think you could get to a 0.5% overhead?
Yeah, 0.5 might be a reach here, but here's...
But then people won't, you can't say that it's okay. You can't say that it's okay to enforce program order because people would just not use it.
No, we are not arguing that you should do this for all the languages. So here, like what we're arguing is that we're arguing this for safe languages like Java. Like if you think about GC, it's not 0.5% overhead for GC. But people choose to pay that cost if they can get memory safety. Yeah.
Okay, Ben,
so I have 2 quick questions. One, did you measure the overhead from de-optimization and compiling twice? And the other one is, do you think that having static race freedom for regions of code will help to combine it so that you don't have to do this for all of the code?
Yes. So about that, I believe you're asking about the startup performance because the de-optimization happens most at the. Okay, you couldn't see the slides now, but basically, because you have to do the de-optimization, it's going to affect your startup performance. The first few iterations is going to be slower, so we actually measure the cost of that. And by looking at that, the speculative approach, it is actually slower than the VBD, than the baseline implementation. And for the number we have, is now it's like 66% for the first iteration. So here again, this approach is going to help you most if your program is non-run in that case. And the second question, I don't know if I remember correctly, but you're asking if there is a relaxed region will help. And we believe that's the case. That is actually part of the work we did for the baseline implementation. We allow people to specify what kind of, for example, we allow them to specify for this specific method, don't do anything and just don't use any fences. And from our evaluation, it actually helped.
All right, let's thank Lynn again for an excellent talk, and please continue the discussions in the breaks.